our recent experiment and numeric simulations. So this is a collaborative job with the Nico Gray. First, I would like to explain some background. Here is the pictures, right? And taken from the Iceland, where there's a high mountain and then got valleys, and here is a town, and then there's the locals set up a deflecting dam which is about 600 meters long, and then on the top is about 20 meters high. On the bottom is about 15 meters high. So, and this part and this valley very frequently have snow avalanches. So the people set up the deflecting dam, try to protect the local areas. So this is the first example. Okay. The second one is also another example from Iceland, another town, and then along the seaside. This is above the mountain, and then it's vulnerable again to the snow avalanches. So they set up a catching dam to protect the town, and then in front of the catching dam, they set up a couple of moles to try to dissipate the avalanche energies before reaching the catching dam. Another one is a test site in Switzerland, and then they set up these pylons and then put the measuring devices to get the pressures, velocities of snow avalanches. So it's anyway, it's quite important to understand when the snow avalanches pass through the obstacles, what would happen. And because the snow avalanches normally travel very fast, so we will expect when the snow avalanches be deflected or stopped by those obstacles, shock waves will be expected. So first, I would like to have a brief explain about the shock wave theory from the continuous. So this is the setup of the chute, and then you got the material. When the material released from the chute, then it pass through the obstacles, we got shock waves to generate it. And the coordinate system can be set up along the downslope direction and the lateral direction. Here is the inclination angle. So accordingly, we can set up the mass and the momentum equation in the shallow water type. And on the right-hand side, we got the source term, which consists of the effect of the gravity, spatial fraction, and also the effect of the topography. Now we move on to the specifically to the shock waves. Here is a sketch of the shock waves when it's passed through a wedge. So this is the flow direction. This is the downslope direction. This is the wedge angle. And then when the shock waves, when the snow avalanches be deflected by this wedge, and the flow will be parallel to the wedge, and then there's a shock wave, oblique shock generated. So you have a shock angle. So basically, the key parameter is the flow number, which is the ratio of the avalanche speed over the sound speed. It is equivalent to the Mach number in the gas dynamics. So from the continuous theory, and then across the shocks, we normally expect the avalanche thickness and the velocity are discontinuous, and also the size of the jumps can be modeled by the jump conditions from the mass equation and the momentum equation. And also, we can measure the loss of the energy across a shock. So from this shock theory, we can, if we ignore the source terms and assume a constant state on either side of the shock, And then we can set up a deflection relation, where this is the deflection angle, this is the shock angle, this is the upstream flow number. So basically, from this relation, it can predict 3 types of shock waves. So see, for a given deflection angle and the upstream flow number, we can have 2 solutions for the deflection angle, and then one we call a strong shock, another is called weak shock, or there's no solution, and then we will expect a detached shock. So this is the picture from the shock solution. So it's gives a relation between the wedge angle and the shock angle. These are the different kind of upstream flow number. And then for each deflection angle, there are 2 solutions. The smaller angle corresponds to the oblique weak shocks, and then the large value of the deflection angle corresponds to the strong shocks. And also, for each upstream flow number, there is a maximum value of the deflection angle. So when this the wedge angle is greater than this maximum angle, and then we'll expect detached shocks. So from this shock relation, and also we can move on to see the detachment of the shocks. So this is if we have a wedge angle, and if we have and then for the different kind of upstream flow number, see for this wedge angle, and then if the upstream flow number is slower enough, and then you will expect a detached shock. And then if the upstream flow travels fast, and then you will see a attached shock. So these are some experiment. From the shock theory, we have 3 types of shocks. One is the weak shock. So this is the generation of the weak shocks, the steady state. So we are looking at the flow moving from left to right, and then it's been deflected by the wedge. So this is the wedge angle, this is the upstream flow number, and this is the inclination angle of the chute. So these are the measurement, and then this is the experiment, the theory and the experiment. So they have a good agreement for the weak shock. And also, there's a strong shock. A strong shock, again, you see here the wedge angle is still the same. The upstream flow number is also the same. But if you can properly control the downstream condition, and then there will be a strong shock generated, which this angle is much wider. And if we look at this comparison between theory and experiment, we see there's a good experiment for the thickness and the velocity, but for the shock angle, in theory, it's much bigger than the experiment. This is because of the effect of the source terms. So this is the numerical simulation result, and this dashed line is predicted by the theory, which is much larger, and then this is the result from the numerical calculation, where you have to control the downstream condition. And also here we see that for the strong shocks, even after shocks, the avalanche thickness still continue increase. And more importantly, for the strong shocks, it can dissipate over 20 times more energy than the weak shock. So these are the 2 types of shocks. So this is the experiment. So normally for this is the wedge angle. If there's no control of the downstream condition, and then we will expect the generation of the weak shock like this. And then if you control the downstream condition, and then there will be a strong shock be generated. So this is another kind of type of shock is called detached shocks. So you can either increase the wedge angle or decrease the upstream flow number. Here you see we increase the wedge angle much bigger than what we've seen before, and then the shocks will have a detachment distance away from the wedge. So this is the generation of the detached shocks. Detached shocks can also dissipate more energy, but less than the strong shock. So now we come to the another part for the snow avalanches. This is the example we explained early, and then we carefully studied we got the digital map of the local area. So this dam is built up in the 1998, and this is the snow avalanches tracks for 1995. So were killed 12 people, and then on 1998 this dam is finished, and after that there are 2 avalanches being deflected on these 2 parts. So this is the our numerical simulation. We try to choose a region where we want to simulate the track or the generation of the shocks along this side. Also, we want to apply the oblique shock theory to see if we can suggest a kind of a designing criterion. If you want to design a dam, what kind of height you should have. So this is the some designing a criterion. We using the field result from the this is the upstream velocity thickness from the field observation, and then give you the flow number, deflection angle for the shocks. So this is based on the jump after the shock. So this is the predicted height of the dam. For the higher part, where the actual height is 20 meters, and the predicted is slightly less than that. And then the lower part got a quite same order of magnitude comparison. So another part we want to simulate the snow avalanches. So this is the deflecting dam. So we are using the field data. This dashed line is the track of the 1999 snow avalanche. So what we are using is the inflow condition provided from the field data, and then we do the numerical simulation. And when these snow avalanches passing through the deflected by the dam, and then you got shock waves, and eventually it's come down to the rest. If you look at the runout region, you will see that there's a big difference between the numerical simulation and the measured tracks. This is, well, one explanation is the inclination angle. You see from the mountain to the flat, the inclination angle will decrease continuously. So on the runout region, so there's some difference. So this is the simulation of the snow avalanches when it is deflected by deflecting dam. So another example is when the snow avalanches, well, we try to stop the snow avalanches by catching dam. So before stopping it, they set up the modes, try to dissipate the energy. So after this dam finished, there is no report yet on the snow avalanches, but we can run some experimental lab experiment. So this is, we choose a simple obstacle. One is the square obstacle. The upstream flow number again is pretty high, like what we did before. So if the flow past one obstacle is flow again from left to right, and then you will expect the shock waves. It's a bow shock. And then if you have 2 obstacles, and then you will expect the shock waves, and then got interaction. And also there is a big effect also on the granular vacuum. So we can carry on to have more allocation of the shocks. Okay, this is a kind of 3 obstacles allocated on different downslope directions, and see you got shocks and then interacted, and again this region will affect the formation of the granular vacuum. So this is another kind of arrangement of the shocks. So interesting, you see that the shocks from the simulation, you see the shape of the shocks are pretty close to the experiment. But another obvious difference, I think, coming from the vacuum. The vacuum here, you got a vacuum, still got a vacuum. But here in numeric simulation, it seems that this region got a stronger effect than the actual experiment, where in the actual experiment, you still see a quite big vacuum, but in experiment, it's already been filled. Okay. And this is another example. You can have a kind of four obstacles to be allocated on two different downslope directions. Again, you can see the more complicated interaction of shocks and also the formation of the granular vacuum. So you see here, you experiment, this is still a kind of looks like symmetric, but here it's got a more interaction is not symmetric. Here it's being filled, and right here you got a vacuum, but not exactly in the similar shape. So this is another example, and where you move the downslope obstacles a little further, and then in the experiment, you got a kind of a symmetric granular vacuum, and the downslope vacuum, this compared well, and this region got more complicated. Okay. So this is the right. Okay. The experiment seems don't run well. This is the numeric simulation. The development again. You see, you basically in the experiment and in the numeric simulation, we only allow let the upstream or inflow condition is exactly the same in experiment, and then we let it run. So this is the numeric simulation. Where when the flow passes around the obstacles, you got shock waves and you got the interaction, and then behind this you got shock waves, and then got the interaction. This region be completely filled, and then you still have some region be left over here. So this is quantitatively, I should say, is still quite similar to this result, where this region you see is filled, and then this region you still feel left a vacuum region. Okay, right. Okay, thank you very much.
Do you have any questions?
Sorry, I didn't understand very well in the previous case when you have the inclined obstacle. You said that for the strong wave you have not control on the outgoing boundary conditions.
For the strong wave.
What do you mean?
For the strong shock, you have to control.
You have to control.
You have to control. Yeah. For the weak shock, you don't need to control. Right.
Okay. And how do you control this?
Basically, it's just mass balance still. Mass balance. You see, you got the upstream. You can have the upstream condition. You got the mass balance, and then the downstream. You control the gate, adjust the height, or to keep the mass balance equivalent. Okay.
For a given density of obstacles, is there one configuration which maximizes the dissipation or not? And can you predict that with this?
That's a good question.
Well,
Yeah.
which one is the best of the that you present? I mean,
Yeah.
you had you had two different configurations for 4 obstacles
Yes.
and 2 different configurations for 3 obstacles.
Yes.
Obviously, 4 obstacles is probably better than 3.
Yes. Yes.
Okay.
Yeah.
And which one of the 4 is it? The alternative or the embrace type of configuration? Yes.
Yeah, that's a good question. I should provide a kind of a more quantitative result. And here, I think this may be able to dissipate more energy than this kind of allocation arrangement, because you see here, and it's closer. If you look at what they did they provided in the picture from Iceland, and you will see the allocations. So you see they don't have a longer distance, so it's just been staggered on 2 different kind of locations. So I believe that kind of arrangement of the obstacles will be able to dissipate more energy.
Okay, I think we have